Carbon dioxide and the Bohr effect. Why do we feel dizzy when we breathe too fast? To answer this question, we need to understand the role of carbon dioxide. First, carbon dioxide plays a significant role in every breath we take. It's a common misconception that we breathe because we are running low on oxygen. We are stimulated to breathe based on how much carbon dioxide is in our blood. The exception is people who have chronic respiratory problems such as emphysema or chronic obstructive pulmonary disease, COPD, who live with abnormally high levels of carbon dioxide and breathe based on low oxygen. As we hold our breath, chemoreceptors sense the decrease in pH and the increase in carbon dioxide, which stimulates us to take the next breath. The higher the carbon dioxide levels, the stronger the desire to breathe. This urge is why it gets harder and harder to hold our breath for a long time. Generally, when we experience that strong urge to breathe, we still have plenty of oxygen in our blood. When I measure my blood oxygen levels while holding my breath, I don't see a drop in oxygen saturation until around 3 minutes of retention, and this is long after I have an urge to breathe. The time it takes for SpO2, peripheral capillary oxygen saturation, to drop varies from person to person and depends on a variety of factors, the main one being how many red blood cells are in the body. As we breathe, the hemoglobin in the red blood cells binds to oxygen as it passes through the lungs, creating oxyhemoglobin. The red blood cells then go out to the body to supply our cells with oxygen. The only problem is that for the red blood cells to release oxygen, oxyhemoglobin needs carbon dioxide to increase blood acidity to facilitate the cellular exchange. This physiological event is called the Bohr Effect, named after Nobel Prize-winning Danish physician Christian Bohr. The Bohr effect states, hemoglobin's oxygen-binding affinity is inversely related both to the acidity and to the concentration of carbon dioxide. Hemoglobin is an iron-rich, oxygen-carrying protein inside red blood cells. There are about 270 million hemoglobin molecules per red blood cell, and each hemoglobin molecule can carry 4 oxygen molecules. That means each red blood cell can hold over 1 billion oxygen molecules. As carbon dioxide levels rise due to cellular respiration, blood pH becomes more acidic, and the bond between the oxygen and hemoglobin is loosened so that oxygen can be released into the cells. If carbon dioxide levels are low and blood pH is high, the red blood cells can't release oxygen into the cells. The body is the ultimate use it or lose it system. Whatever we do, our bodies work to support us. If we run, our bodies will work in a way to help us become better at running. Our leg muscles will get stronger, our tendons will become more bouncy and elastic, and our endurance will increase. If we practice sitting on the couch, our bodies are going to get really good at sitting on the couch. The body's main concern is survival, and our survival is dependent on having the energy to fuel the body as well as store reserves to get more energy when fuel starts to run low. Muscles take a lot of energy, which is why our muscles atrophy when we stop exercising. Fat is the body's way to store energy, which is why it stores any excess it receives as adipose tissue. Every second, approximately 2 to 2.5 million of our red blood cells die, and about the same number are created in our bone marrow to replace them. Those red blood cells will live for 3 to 4 months before they are replaced with new ones based on the body's current demands. Current demands are important to understand. Our body's response to what we've been doing, it doesn't know what we're going to need to do. If we are breathing too much, our carbon dioxide levels stay low and the red blood cells can't release oxygen. As a result, the body thinks it has too many red blood cells, so it doesn't replace them when they die. We are then left with the bare minimum number of red blood cells we need to survive. In this state, if we decided to go for a run, we would get winded quickly. Chronic overbreathers also can't hold their breath very long. When they do, their SpO2 levels drop quickly because they don't have extra red blood cells circulating to meet the new demand. So, carbon dioxide stimulates us to breathe and allows oxygen to be released from the red blood cells so that it can be used by the muscles, organs, and every other cell in the body. Carbon dioxide also opens our airways, which is called bronchodilation, so we can breathe better. It expands our blood vessels, called vasodilation, which lowers blood pressure and allows the blood to perfuse our extremities with less effort by the heart. The opposite happens when carbon dioxide levels are low, a state known as hypocapnia. Our airways get smaller and our blood vessels constrict. As carbon dioxide levels decrease, the blood vessels going to the brain constrict. In turn, the brain receives significantly less blood and oxygen, which is why we feel lightheaded and dizzy when we hyperventilate. This familiar response is not from too much oxygen, it's from too little. Bringing more oxygen into the brain makes us feel clear, aware, and focused. Increasing carbon dioxide levels through breathing less offers many amazing benefits, which is why so many of the practices in this book are focused on holding the breath, slowing components of the breath, or simply creating good habits of breathing less. The majority of people who overbreathe are not aware they do it. When you go out in public, notice how many people are breathing through their mouths. Anyone who is mouth breathing is overbreathing. The nose creates about 50% more airflow restriction than the mouth. In other words, if we are breathing through our mouths, we are breathing twice as much as we should, and it's a downward spiral from there. Mouth breathing leads to lower levels of carbon dioxide, which means the red blood cells can't release oxygen into our tissues, and our cells aren't adequately perfused. The red blood cells return to the lungs still carrying their full oxygen load. The body recognizes this as a waste of energy, and since making new red blood cells takes energy, it doesn't replace those returning cells because it doesn't think it needs to. This means less oxygen-carrying hemoglobin, which means anytime we do anything, we'll need to breathe faster and deeper, which again lowers carbon dioxide levels. Unfortunately, this cycle continues. To summarize the carbon dioxide and Bohr effect, oxygen has a strong affinity to hemoglobin, the oxygen-carrying protein component of the red blood cells. This affinity allows oxygen to bind to hemoglobin in the lungs easily. When the oxygen gets to the tissues, it needs to be able to be released from the red blood cells. As carbon dioxide increases in the tissues and blood pH decreases. The decrease in pH lowers oxygen's affinity to hemoglobin, and the oxygen is released to fuel the cells. The Bohr effect shows that higher carbon dioxide levels and a lower blood pH create better oxygenation of tissues.